Okay, good morning to Dr. Nordin and everyone. Let's begin my presentation. Today I will present about fluid feature and dimensional analysis concepts. I'm Po Xuet Lian, metric number 208544. For the fluid mechanics, fluid can be defined as a substance which can deform continuously when being subjected to shear stress at any magnitude. In other words, it can flow continuously as a result of shearing actions. These include any liquid or gases. There are 5 fluid properties, that is, density, specific weight, specific gravity, viscosity, and surface tension. For the fluid property of density, the formula is mass over volume, m over v. Unit is kilogram per meter cube. Definition is mass per unit volume, slightly affected by change in temperature and pressure. For the typical value or the example of water is 1 gram per cm cube, and A is 1.23 kilogram per meter cube. For the specific weight, the formula is equal to rho U. Unit is Newton per meter cube. Definition is weight of a fluid per unit volume. The typical value or the example is water equal to 9,814 Newton per meter cube. A is equal to 12.07 Newton per meter cube. So for the specific gravity, unit is dimensionless. The definition is a ratio of the density of a liquid to the density of water at standard temperature and pressure at 20 degree and 1 atm, or a ratio of the specific weight of a liquid to the specific weight of water at standard temperature and pressure at 20 degrees Celsius and 1 atm. For the viscosity, unit is equal to Newton times S per meter cube or kilogram per meter per second. The definition is the viscosity of a fluid measured is resistant to flow under an applied shear stress. The example is water equal to 1.14 times 10 power of negative 3 kilogram per meter per second. A equal to 1.78 times 10 power of 5 times 10 power of negative 5 kilogram per meter per second. As two type of viscosity. One is dynamic viscosity and kinetic viscosity. So the unit is Newton times second over meter cube or Pascal, second or kilogram per meter second. For the kinetic viscosity is unit equal to meter square per second. And here is the formula. This is the formula to calculate the dynamic viscosity and kinetic viscosity. For the surface tension is equal to force over length. Units is equal to Newton per meter. Definition is the property of the surface of a liquid that allows it to resist an external force due to the cohesive nature of the water molecule. So for the Newton fluid, for this type of fluid, there is a linear relationship between shear stress and the velocity gradient. So we can look at the graph here. It's all in linear graph, linear lines. The dynamic viscosity is the slope of the line here. Dynamic viscosity is also constant for a fluid at the same temperature. As temperature increases, dynamic viscosity decreases, so the slope decreases. The most common fluid are, for example, is air, water, oil. For the non-Newtonian fluid, for this type of fluid, there is no linear relationship between shear stress and the velocity gradients, and the slope of the curve is very. So the line at the graph here is all in the curve form. The general relation is equal to A plus B dv over dy times m. The value of A, B, and n depends on the types of non-Newtonian fluid. So for the surface stress and elastic modulus, the formula of the elastic modulus is equal to stress over strain. The definition is measure of the stiffness of a material under compression or tensions. So the formula of stress is equal to force over area. So the unit is Pascal or Newton per meter cube or Newton per millimeter cube. So the strain is equal to the change in length over original length, and the unit is dimensionless. So for the elastic modulus, the unit is Pascal or Newton per meter square or Newton per millimeter square. And here is the graph for the elastic modulus. So the modulus of elasticity is also called elastic modulus, is the measurement of material elasticity. Elastic modulus quantity of material resistant to non-permanence or elastic deformation. When under stress, material will first exhibit elastic property. The stress causes them to deform, but the material will return to its previous state after the stress is removed. After passing through the elastic region and through the yield point, material enter a plastic region, where they exhibit permanent deformations even after the tensile stress is removed. So here is the elastic deformation. Here is the plastic. After here is the plastic deformation, and when it reaches here is a fracture point. This is the compressibility of fluid and vapor pressure. So we can see when the fluid outflow, the volume of the fluid is decreases, and when the fluid inflow, the volume of the fluid is increases. And the compressibility is the measure of the change in its volume a sustain undergoes when a pressure is exerted on the sustain. Liquids are generally considered to be incompressible. Gases are very compressible. The volume of a gas can be readily changed by existing an external pressure on the gas. So for the vapor pressure is a measure of the tendency of a material to change into the gaseous or vapor state and is increased with temperature. This pressure is formed in a thermodynamic equilibrium state in a closed container at a certain temperature. The temperature at which the vapor pressure at the surface of a liquid becomes equal to the pressure exerted by the surrounding is called the boiling point of the liquid. So, at the evaporation state, bubble cannot form since the vapor pressure is less than atmospheric pressure. At boiling state, the bubble can form and rest since the vapor pressure can overcome atmospheric pressure. And in a closed system, evaporation which has reached equilibrium with the liquid surface is said to have reached the saturation. The characteristic of vapor pressure is a pure liquid experiences a greater amount of vapor pressure as against a liquid solution. It is inversely proportional to the force of attraction existing between the molecules of a liquid. Its increase will rise in the temperature. This is because the molecule gains kinetic energy and thus vaporize briefly. So for the dimensional analysis and modeling, the definition of dimension is a measure of a physical quantity. In an FT system, mass is equal to m, length L times is equal to T. At the FLT system, force is equal to MLT, power of negative 2, length is L, time is equal to T. So the dimension homogeneity, every additive term in an equation must have the same dimension. For the displacement of a falling body, z equal to z0 plus v0t minus 1 over 2 gt squared. L is equal to L plus L over T times T minus L over T squared times T squared. So we can cancel it here. And it will become L. And it will equal to L. The z0 is equal to initial distance at t equal to 0. The v0 is equal to initial velocity. So this is the falling object. V is equal to component of velocity in z directions. Z is equal to the vertical distance. G is equal to gravitational acceleration in the negative z directions. So for the dimensional analysis, a method for reducing the number and complexity of experimental variables that affect a given physical phenomena. First is reduce the number of variables. Suppose the force F on a particular body shape immersed in a stream of fluid depends only on the body length L, velocity V, fluid density, and viscosity. So, using dimensional analysis, we can reduce the parameter to only one. F is equal to the fluid density times length square times v square is equal to gravitational acceleration times density times velocity times length over viscosity is equal to gravitational accelerations Re. So for the non-dimensional equations that will provide insight on the controlling parameter and the nature of the problem. And the scaling law, that's a load testing model instead of expensive large full-scale prototype. So the REM is equal to REP. FP over FM is equal to rho P over rho M times VP over VM square times length P over length M square. Okay. For the dimensional similarity is concerned with how to transfer measurements from model to the full scale. Three types of similarity which exist between a model and prototype. First is geometric similarity. The ratio of all corresponding dimensions in the model and prototype are equal. L model over L prototype is equal to Ln over Lv is equal to lambda L. A model over A prototype is equal to L square M over L square P is equal to lambda square L. So we can see in the picture here the 40 meter is equal to 4 meter. The L meter is the 1 meter is equal to 0.1 meter. the 8 meter is equal to 0.8 meter. So the ratio of the corresponding dimension in the model and the prototypes are equal. The kinematic similarity, the similarity of times as well as geometric, is as if the path of particles are geometrically similar and the ratio of the velocity are similar. And here is the dynamic similarity. Dynamic similarity exists when the model and the prototype have the same length scale ratio, time scale ratio, and the force scale ratio. Dynamic similarity exists simultaneously with kinematic similarity if the model and prototype force and pressure coefficients are identical. So if the model and prototype are geometrically similar and if its independent dimensionless parameter for the model is equal to the corresponding independent dimensionless parameter of the prototype, then the independent dimensionless parameter for the prototype will be equal to the corresponding dependent dimensionless for the model. So the Buckingham-Pi theorems is state that if there are n variables in a problem and this variable contains m primary dimensions, for example MLT, the equation relating all the variables will have m and m dimensionless group. This method offers the advantage of being more simple than the method of solving simultaneous equations for obtaining the value of the index. For the obtaining the value of the index, the exponent value of the variable. In this method of solving the equation, there are two conditions. A is of the fundamental dimensions must appear in at least one of the m variables. B is must not be possible to form a dimensionless group from one of the variables within a recurring set. A recurring set is a group of variables forming a dimensionless group. The method of repeating variables. Step 1 lists all the variables that are involved in the problem. Step 2 express each of the variables in terms of basic dimension. Step 3 determine the required number of pi terms. Step 4 select a number of repeating variables where the number required is equal to the number of reference dimensions. Step 5 form a pi term by multiplying one of the non-repeating variable by the product of the repeating variable. Each raised to an exponent that will make the combination dimensionless. Step 6 repeat step 5 each of the remaining non-repeating variable. Step 7 check all the resulting pi terms to make sure they are dimensionless. Step 8 express the final form as a relationship among the pi terms and think about what it means. So here is the table for the reference of the FLT system and MLT system. Okay, example 1. The pressure drop along a straight pipe of diameter D has been experimentally studied, and it is observed that for laminar flow of a given fluid and pipe, the pressure drop vary directly with the distance L between pressure taps. Assume that pressure drop is a function of diameter and length, the velocity v, and the fluid viscosity. Use dimensional analysis to deduct how the pressure drop vary with pipe diameter. So, step 1 lists all the variables that are involved in the problem. So, this is the pressure drop is equal to F diameter, length, velocity, and viscosity. express each of the variable in terms of basic dimensions. So pressure drop is equal to m over meter square. Dimension is m over l t m over l t square. D, the unit of D is m and the dimension is l. Same as the length, unit is m and dimension is l. For the velocity, unit is meter per second, the dimension is l per t. For the viscosity, unit is Newton times second per meter square, so the dimension is meter m over l t. Step 3, determine the required number of pi terms. M equal to 5 for pressure drop, diameter, length, velocity, and viscosity. M equal to 3 for MLT. So R is equal to N minus M is equal to 5 minus 2 is 2. Is 2 pi term. Select a number of repeating variable where the number required is equal to the number of reference dimension. So diameter, velocity, and viscosity is for length times is for L, M, and T respectively. So step 5 is equal to combine diameter, velocity, viscosity with one additional variable, pressure drop or length in sequence to find the 2 pi product. It's equal to d power of A, v power of B, viscosity power of C, and pressure drop is equal to L power of A, L over T power of B, M power L T power of C, M per L T power of C, M per L T square is equal to M. We have C and C and 1 right here. And L is A, B, negative C, negative 1 times C, and minus L, minus 1. T is negative B, negative C, negative 2, is equal to M0, L0, T0. Its square exponent mass is equal to C plus 1 is equal to 0, but we know C is equal to negative 1. So for the times, we can calculate B once we know the answer of C. Negative B minus 1 minus 2 is equal to 0. Negative B plus 1 minus 2 is equal to 0. B is equal to negative 1. A plus negative 1 minus negative 1 minus 1 is equal to 0. A minus 2 plus 1 is equal to 0. A is equal to 1. Therefore, D V power of negative 1, viscosity power of negative 1, pressure drop is equal to pressure drop times diameter over viscosity times velocity. So step 6 repeat step 5 for each of the remaining non-repeating variable. So it's equal to D power of A, V power of B, viscosity power of C, and length is equal to length power of A, L over T power of B, M L per T power of B, M per L T power of C, and L. So M is C, M1 times C is C. L, A, 1 times B, A plus B minus C and 1 plus 1. T is minus 1. Negative 1 times B is equal to negative B, and negative 1 times C is equal to negative C. So it's equal to M0, L0, T0. Is for the squared exponent, mass is equal to C equal to 0. So we can calculate the mass C is equal to 0 times negative B, negative 0 is equal to B is equal to 0. A plus 0 minus 0 plus 1 is equal to 0. A equal to negative 1. So, therefore, D power of negative 1, V power of 0, viscosity power of 0, and length is equal to length over diameter. So, step 7 checks all the resulting pi term. For the pressure drop, the unit is Newton per meter square. Diameter and length unit is meter. V is meter per second. Viscosity is Newton times S per meter square. The dimension is of pressure drop is F over F per L square. D and length is same dimension is L. V is L per T. Viscosity is F times T over L squared. So, pressure drop times diameter over viscosity times velocity is equal to FL power of negative 2 times L over FTL power of negative 2 L T negative 1 is equal to F0 L0 T0. And for the second one, length over D is equal to L over L is equal to F0 L0 T0. So express the final form as a relationship among the pi terms. So pi 1 is equal to F pi 2, or pressure drop times diameter over viscosity times velocity is equal to F times length over diameter. Think about what it means since pressure drops alpha length, so pressure drop times diameter over viscosity times velocity is equal to C dot C times length over D, where C is a constant. Thus, pressure drops alpha 1 over D squared. Okay. So the last one, dimensionless terms, and here is the common dimensionless group in fluid mechanics. This is Reynolds number, Proust number, Euler number, Cauchy number, Marsh number, Stokes number, and Weber number. And this is the formula and the applications with interpretations. So that's all is my presentations. Thank you everyone.